Okay, I'm recording now. Okay, people who wanted the recording, I'm very sorry. You just missed 150. So I'll kind of scroll through this nice and slow. Dun, dun, dun. You can also ask somebody who's here, okay? So there you go. That's 150. Hopefully you can follow all that. You can pause the video probably. Okay, and then the other question was 152, right?
Yes.
152. Okay, a 2.52 gram sample of a compound containing only carbon, hydrogen, nitrogen, oxygen, and sulfur is burned in excess oxygen to yield 4.23 grams of CO2, 1.01 gram of H2O. Another sample of the same compound of mass 4.14 gram yields 2.11 grams of SO3. A third sample of mass 5.66 gram yields 2.27 grams of nitric acid. Calculate the empirical formula of the compound. Okay, so we have some compound that we're burning and reacting with different things to form different products. And this compound is formed with carbon, oops. Let's see, carbon, hydrogen, nitrogen, and oxygen. Okay, so it has these four elements kind of stuck together in some arrangement, and our task is to find the empirical formula for the compound. Okay, so there's a couple tests that happen here. Oh wait, no, we also have sulfur. Sorry, can't miss sulfur. A couple tests that happen here. The first test is burned in excess oxygen to yield okay, so when they burned it in excess CO2, we yielded 4.23 grams of CO2 and 1.01 grams of H2O. And this came from a 2.52 gram sample. So that was the first thing. The second thing was mass 4.14 grams, and we made 2.11 grams of SO3. And then a third experiment of 5.66 grams yielded 2.27 grams of nitric acid. Okay, and then our goal is to calculate the empirical formula for this compound. Okay, so what we need to do here is we need to find out the percentage of carbon that's in this mass here. Okay, I'm going to start with the first experiment. I want to determine the percentage of carbon that's in this original mass based on the percent mass of CO2 itself. Okay, so the percent mass of CO2, I'm going to use the percent mass of carbon in CO2 to get the mass of total carbon that was produced here rather than the mass of CO2. Okay, so we need the percent mass of carbon in CO2. Percent mass of carbon in CO2 is found by just dividing the atomic mass of carbon, which is 12.01 grams per mole, divided by the molecular weight of carbon dioxide, which is 44.01 grams per mole, multiplied by 100%. Grams per mole cancels out, and we get 27.289%. Dang it. OneNote crashed. Sorry. What a day.
It couldn't handle it.
It couldn't handle it. It started seeing percent masses and it was just like, just blew up on us. Okay, what did I say that was? This is equal to 27.289% carbon. Okay, now I can use this percent mass up here with this 4.23 grams of CO2 to calculate how much of that mass is actually carbon. Okay, so I'm just going to multiply that mass by the decimal form, so 0.27287, and I get a total mass, a total carbon mass of I have to calculate this, 4.23 times 0.27287. 1.154, and let's see, that's 4 sig figs, that's 3, so we end up with 3 here. 1.154 grams of carbon. And we're going to do the same thing for, let's see, the hydrogen, the percent of hydrogen in H2O. Okay, so percent mass hydrogen in H2O.
Just another quick question. You did the carbon and the hydrogen because the oxygen was burned.
Yeah, so in this case, the oxygen is always in excess, which means that all of the oxygen that I'm getting from the burning process, basically any of the oxygen that's coming in here, I can't trust the mass of it because I'm getting so much oxygen from the environment. So the only way that I'm going to be able to figure out the percentage of oxygen in the final empirical formula is to do a subtraction from 100. So my goal here is to get all 4 of the others, add them together, and then subtract from 100, because all of these are in the presence of oxygen. So there's no way I can separate it out other than subtracting it from 100.
Right, I got you.
Okay, so hydrogen in water. We need the percent mass of hydrogen in water. This would be 2 times 1.01 grams per mole, divided by the total molecular weight of water, which is 18.02 grams per mole, we'll say, something like that, times 100%. And that ends up being 11.209%. Okay, so now I just come up here to the mass of water that we got, and we multiply this by the mass of hydrogen, because again, I only trust the hydrogen here. I don't trust the oxygen because everything is in excess of oxygen. So now I just take this and I multiply it by the decimal value here, which is 11209, and I get 0.01256. And that's also 3 sig figs. Okay, now the reason I'm going through all of this trouble to find the mass of carbon and the mass of hydrogen is because I want to compare these masses with the mass of the original sample and see what percentage of the original sample the individual components are. Okay, so right now I started with 2.52 grams of sample and I got 1.154 grams of carbon and 0.01256 grams of hydrogen. So now I want to calculate the percentage that is of the original sample. And that would give me, necessarily gives me the percentage it is of the original compound. Okay, so I'm going to write all of this. Let's see, where can I write it? Let's write it over here somewhere. So carbon percent hydrogen, percent sulfur, percent nitrogen, and percent oxygen. Okay, so the percent carbon in this case, all I have to do is take this total mass, 2.52 grams, or the mass of carbon, 1.154, divide it by the total mass and multiply by 100, and that gives me the percent carbon. So that would be 1.154 divided by 2.52. Is that right? 2.52, yep, that's right. Multiplied by 100. So this compound, this unknown compound is 45.79% carbon. Oops, 79. Man, I screwed that all up. 45.793% carbon. And we could do the same thing with hydrogen here. So 0.01256 divided by 2.52 to get the percent of hydrogen by mass. So that would be 0.01256 divided by 2.52 is equal to 0.4984% hydrogen. Okay, moving on. Let's look at the next experiment to see if we can figure out sulfur. Okay, so for the next experiment, 4.14 grams of this stuff were burned, and they got out 2.11 grams of SO3. Okay, so just like with the CO2 and the H2O, I need to calculate the mass percentage of sulfur in SO3 so I can get the total mass of sulfur that was produced here, because again, I don't trust the oxygen. So here it is, percent mass of sulfur in SO3. Okay, so here there's one sulfur in SO3, and sulfur is 32.06 divided by 32.06 plus 3 times 16, and that gives us 80.06. Does everybody see what I'm doing here? I don't want to skip too fast, but if you don't see what I'm doing here, just let me know. Raise your hand.
How did you do that 80.06 again?
So this is the molecular weight of SO3. So I'm just adding up the atomic weights for all of the pieces. So that would be sulfur's atomic mass, which is 32.06, plus 3 times oxygen's atomic mass, which is 16.
Oh, okay.
Okay, then we multiply this by 100, and we get 32.06 divided by 80.06. And that is equal to 40.04. Okay, so this stuff is 40.04, 4% sulfur by mass. So if we go up here and we multiply this 4.14 grams by the decimal value, sorry, the 2.11 grams, not the 4.14. Multiply the 2.11 grams of SO3 by that 40%, and we find that we create a mass of 0.8449 grams of sulfur. Okay, so now we have the mass of sulfur we made. We have the total mass that we put in, 4.14. We can calculate the percent sulfur in the original product. Is 0.8449 divided by 4.14 times 100. And this gives us the percent mass of sulfur in the original compound. 0.8449 divided by 4.14, and that gives us 20.40%. Those all have 3 significant figures. Okay, we've got 3, 2 to go. So the next thing we're going to tackle is nitrogen in HNO3. Okay, so we need to calculate the mass percent just like we've done before for the others. Nitrogen in HNO3. Okay, so nitrogen, its atomic mass is 14.01 grams per mole. And then we're going to divide that by the total molecular weight of HNO3. So that would be, H would be 1.01 grams per mole, plus N would be 14.01 grams per mole, plus O3 would be 3 times 16.00. And let's see, that would equal 63.02. So we have 14.01 divided by 63.02 times 100, and this equals 22.231%. Okay, so HNO or nitrogen is 22.23% by mass of nitric acid. So we go up here to the experiment where we got the nitric acid, and we multiply it by its decimal. So this 2.77 grams. Oh, that's a 2. 2.27 grams. So 2.27 times okay, so then 0.20, what was this? Oh no, it was 2223. Is equal to 0.5046 grams of nitrogen. So then we can take this value, and we can calculate the total percentage of nitrogen in the compound. .5046 times 100. Okay, that turns out to be 8.9151. And that's also 3 sig fig, so we'll stop there, percent. Okay, now we can figure out the percentage of oxygen just by subtracting by 100. So we have all of these amounts here. So let's just add them up real quick. This would be 45.793 plus 0.4984 plus 20.408 plus 8.9151. Okay, so all of that equals 75.6145%. Okay, 75.6145%. And if we take that out of 100, we end up with 24.385% oxygen. Does everybody see what I did there? And as a matter of fact, since I'm adding all these up, I think I can only keep to this digit. So yeah, so I have to that digit, 3 sig figs still. Okay, so now I have the percentages of all of the compounds. This doesn't really help me right away because I want to get the empirical formula, and the empirical formula has to do with the moles of the thing. Okay, so we have to convert these values into moles of each of their constituent before we plug them in for the empirical formula. The way that we're going to do this is we're going to say, since these are all percentages, we can just say that we have a 100-gram sample. If we have a 100-gram sample, that means that 45 point, oh gosh, that's really bad. Sorry. In a 100-gram sample, we have 45.798, oops, 93. I don't even need the 3. 45.79 grams of carbon, and I can convert that into a mole of carbon using its molar mass. So I multiply by the inverse molar mass, which would be 1 mole divided by 12.01 grams. So now I have the moles of carbon in a 100-gram sample, and that equals to 45.79 divided by 12.01 is equal to 3.81 moles. Okay, let's put another number on there, 3.812. There we go. Now I can do the same thing for everything else. I'm going to have exactly 0.4984 grams of hydrogen. Multiply that by its inverse molar mass. 1 mole of hydrogen is equal to 1.0 grams of hydrogen. Grams cancels out, and I end up with 0.4984 divided by 1.01, and I get 0.49346 moles of oxygen. Okay, next, what is this? Is this sulfur? Yeah. So if I have 20.41 grams of sulfur, I multiply this by sulfur's molar or atomic mass, which is 32.01, right? Or 32.06. Oops, inverse. 1 mole divided by 32.06 grams. Grams cancel out. So we end up with 20.40 divided by 32.06. And that ends up being 0.6363 moles of sulfur. Next is nitrogen. So I have 8.915 grams of nitrogen. I'm going to multiply that by the inverse molar mass of nitrogen, 1 mole divided by 14.01 grams. And I end up with grams canceling out. So that'd be 8.915 divided by 14.01. 0.6363. 0.6363 moles of nitrogen as well. And then oxygen is 24.385 grams. Oops, the 20 or the 3 is the sig fig. So we'll just call that 24.39 grams of oxygen multiplied by inverse molar mass, 1 mole over. No. Dang it, we were so close. One note. I don't know what its problem is. Oh, did it erase all that? Okay, well, I can remember what nitrogen was. It was 6363. It was the same as sulfur. Okay, oxygen. Here we have 24.39, we'll say, grams of oxygen multiplied by the inverse molar mass of oxygen. So that'd be 1 mole divided by 16.00 grams. Grams cancels out, and we end up with 24.39 divided by 16.00, and we get 1.524 moles. Good to 3 sig figs. Okay, now we have all the moles, and we can put this together in a pseudo empirical formula. So we have carbon 3.812, hydrogen 0.4. Are you serious? Dang it. Come on, OneNote. I can't. We're so close. Oh, look, we're losing a little bit of data every time. Maybe it's because I'm going too far to the right. Maybe it doesn't like that. Let's go down instead. Let's try that out. I don't know. Maybe it'll work. We have to make the pseudo formula. So that would be carbon 3.812. Hydrogen 0.4935. Nitrogen 0.6363. Oxygen, sulfur 0.6363. Oxygen 1.524. Okay, so the way that we get this from a pseudo formula into an actual empirical formula is by dividing by the smallest amount. So the smallest amount here is the hydrogen. So I'm going to divide everything by 0.4935, 0.4935, 0.4935, 0.4935, and 0.4935. So from this we get carbon 3.812 divided by 0.4935 is equal to 7.72. Oh, that's not right. Sorry. 3.812 divided by 0.4935. Oh yeah, that is right. Sorry. 7.72. 4. And then we have hydrogen 1, nitrogen 1.289. sulfur 1.289, and oxygen 3.088. Okay, so these are not whole numbers yet. We have one more trick that we have to do. And let me just look this up real quick. I want to make sure that we're close. I think we messed up somewhere. Hang on a second. This should have worked out better than this. Probably a math mistake somewhere. Okay, so for the hydrogen, oops, okay, this wasn't 0.4984, it was 4.984. That was the mistake I made. Whoops. So the percentage here is 4.984% hydrogen. That would necessarily change the percentage of oxygen here. So let's recalculate that. So that would be 100 minus 45.793 minus 4.984 minus 20.408 minus 8.9151 is 19.89% oxygen. Okay, the rest of them are good, I think. Let's double check them real quick though. Sulfur 20.41, yes. Nitrogen 8.92, yes. Okay, we're good. Okay, so now we need to recalculate the moles of hydrogen real quick. So that would be, instead of 0.4395, that would be 4. What is it? Dang it, 4.984 divided by 1.01, 4.935. Okay, and then the number of moles of oxygen here is also going to change. So that's not 20.39 anymore. That is 19.89. Okay, so 19.89 divided by 16 is equal to 1.243. Okay. Let's erase all of this nonsense. By the way that I figured out that something was wrong was that it didn't work out like it should have there once I divided by the smallest number. Everything should start to kind of cancel out and become close to whole numbers once you divide out the lowest number. So if you're doing a problem like this and this happens to you, you likely have an issue with your percentages. So just go back and double check those. Okay, so carbon doesn't change, hydrogen does change. That would be 4.935%. And then oxygen also changes. This is 1.2 or 243 moles. Okay, now we're going to divide by the smallest number, which is the number of moles of nitrogen and sulfur. So each of these I'm going to divide by 0.6363. So carbon 3.812 divided by 0.6363 is equal to 5.999999. So that's 6. Hydrogen 4.935 divided by 0.6363 is equal to 7.75. Wait, did I do that wrong again? What the heck? Can you guys hear my kids singing?
I can't make out what they're singing.
You can hear it though. I think they're doing some sort of opera. I don't know. I don't know what's going on.
It's beautiful.
I'll tell them you said so. They'll be tickled pink by that. Huh. 4.445. This is not 4.935, it's 4.445. Goodness, making a lot of mistakes tonight. Okay, 4.445 divided by 0.6363 is equal to 6.986, which is 7. Nitrogen, of course, has 1, so does sulfur. And then oxygen here, 1.293 divided by 0.6363 is equal to 2.01. Oh, okay. There we go. This is the empirical formula for the compound. What a problem. That's a tough one. I like it. So a problem like this is really time consuming. So you never really have to worry about something like this being on the exam, just because it would take up the entire period for you guys to do it. I mean, it took me, I don't know, 30 minutes to solve this one. I would never put something this intense on an exam, but pieces of it are things that you should know. So it kind of is like put together a bunch of all of the different pieces that we kind of learned in this whole chapter come together in this one problem. And that's why I like to use these types of problems in the homework, because it kind of forces you to learn all of the different aspects. But rest assured, I'm never, ever, ever going to ask a question like this on an exam. This is just too much. But it's really fun to do for homework, right? Okay, let's see. We have 3 minutes left. Anybody have any questions they want to ask?
I have a question about number 66.
Okay.
How do you find how many molecules or formula units?
Let's see. 6. Okay, so you're given a mass. Let's do A together. So this is number. Let me scroll all the way over. Goodness gracious, that was such a massive problem. Okay, finally, number 68. It asks you how many molecules or formula units are in each sample. Okay, so what it's asking you to do is figure out how many molecules are in the given sample. So for example, A, it's asking how many molecules of carbon tetrachloride are there in this 85.26 gram sample.
I meant number 66.
Oh.
I'm sorry.
Did you say 66 and I just started doing 68?
I think so. I don't think 68 is on it.
Oh, I'm okay. I'm actually doing 66, but I wrote down 68 like a ninja.
Oh, okay.
Yeah, sorry. Sorry about that. Okay. Number 66. I'm actually doing number 66 though. We're good. Wait, you asked about 66, right? Okay. Okay. Good. So we're given this sample 85.26 grams of carbon tetrachloride. And it asks us how many molecules are in this sample. The first thing we need to do here is convert this into the number of moles. Okay, and the way that we convert into moles is by using the molar mass. So the molar mass of carbon tetrachloride is just going to be the sum of the atomic masses of each of these individual pieces. So the molecular weight or the formula weight would be 12.01 grams per mole plus 4 times 35.45 grams per mole. And we end up with 153.81 grams per mole. Okay, so we take 85.26 grams and we want to multiply it by the inverse of this so that we can get it in the moles. So this is 1 mole per 153.81 grams. Okay, grams cancel out and I'm left with moles here. So this is 85.26 divided by 153.81. Can you guys hear my kids? I think that they're in the shower. I think that's what's going on. They're singing in the shower. This is hilarious. Okay, so we end up with the total number of moles 0.554 moles of CCl4. Okay, so now we have the moles of CCl4. To get from moles to molecules, we need to use Avogadro's number because that tells us how many molecules are in 1 mole of that compound. So to go from moles to number of molecules, all we have to do is multiply by Avogadro's number. So this would be 0.554 moles of, no, dang it. Okay, it's gonna open back up here for me. I don't know what's going on with OneNote. I think I need to update my computer or something. Okay, right where we started. 0.554 moles of carbon tetrachloride multiplied by Avogadro's number, which is 6.022 times 10 to the 23rd molecules per mole. Okay, moles cancels out here, and I'm left with times 6.02, 3.338 times 10 to the 23rd CCl4 molecules. And let's do sig figs here. So that would be 85.26. That's 4. So we should have 4 all the way through. Yeah. So it should be 3.338 times 10 to the 23rd carbon tetrachloride molecules.
Okay, thank you.
You're welcome. And the rest of them are basically the same idea, just follow the same principles. For the ionic ones, so for example, for B, instead of calculating per molecule, calculate per formula unit, which in this case would be given by NaHCO3.
What makes it different?
So in an ionic compound, the formula units in and of themselves don't exist as singular molecules. It's more like trillions of these sodium atoms and trillions of these bicarbonate atoms, polyatomic ions, are kind of stuck together in a large crystal. That's how they exist. And the formula unit is basically the smallest subunit of that large crystal. So anytime it's an ionic compound, it exists as a large crystal, which you then talk about formula units as the smallest distinguishable part of this large crystal. Whereas with a molecule, a compound, each individual molecule is only bound to itself and can exist by itself. So it's a little bit separate. It's separate than a large macro crystal that you would form with an ionic compound.
Would you do anything different with that one, or would you do the same steps?
Nope, you do the exact same steps. So for this, for example, in B, if I have 55.93 grams of sodium bicarbonate, okay, that means that I want to convert this into moles first. So I need to calculate the molar mass of sodium bicarbonate. And so you would sum up the masses of all of the atoms that go into this formula unit to get your molecular weight, just like you would if it was a molecule. And then once you have the moles, then you use Avogadro's number, just like you would if you had a molecule.
And also, since it's the only one that's kilograms, would you just convert it to grams and then to moles?
Yeah, so I would convert it into grams first, and then use the molar weight to convert into moles. Yeah.
Okay.
Yeah, good catch. I didn't even see the kilogram there. Tricky. Okay.
So you would solve it the same way, but then would your answer be, would you just put down like formula units as your, I don't know,
Yeah.
classifier instead of molecules?
Yes, exactly. Because this technically is not a molecule.
So it's only classified as a molecule when it's just two put together?
No, it's only classified as a molecule when it is composed of covalent bonds. So it has to do with the type of bonding that's happening here. So for example, here, this is carbon that's attached to 4 chlorines. And each of these bonds are covalent. And we know that they're covalent because both carbon and chlorine are nonmetals. And so when you form any type of bond between nonmetals, it's going to be covalent. And always when you form a covalent bond, you have a molecule. But in the case of sodium bicarbonate, you have a ionic bond that forms between the two ions. So you have sodium here and HCO3 minus, and they're going to be bound to each other just due to electrostatic attraction.
Okay. So if it's with like, so is that a polyatomic ion?
Yeah.
Okay, so if one's with that, then it would be ionic.
If one's with that, you mean like if you mean like the sodium?
An element is with polyatomic ion, would it be ionic?
Yeah, so the bond between these two ions is ionic. Okay. The bond between those two is ionic, but, and this is where it gets kind of complicated, the bond between carbon, oxygen, in CO3, oh wait, this is another one out here, I think, something like that. I think that's the structure. The bonds within that polyatomic ion are covalent, just to make it a little bit more confusing. So you can have a compound that contains both covalent and ionic bonds. Just wanted to point that out.
Okay.
Okay, guys. I gotta go see what my kids were singing about. Anybody have any last quick questions? No? Okay, cool. Well, I hope you guys have a great Wednesday evening, and I'll see you, if not in lab before then, I'll see you on Friday.
Thank you.
You're welcome.
Have a good night.
You too.
Bye.
Bye.